Bismillahirrahmanirrahim. Welcome to Lecture 3. This lecture is basically about sequential circuits and in particularly two fundamental blocks. One is D-Latch and the other is D flip-flop. So this is the outline of the presentation. So we have two main topics as I told you. So what is a D-Latch? Let me go back to here just to introduce them both. So D-Latch, you can say, is like a box which has D, Q, and sometimes this is called gate, and this is Q prime or Q bar, and the behavior, this G is sometimes also called clock, although it should be called gate, but in this book they also call it clock. So let's say it can be gate or clock. So the behavior is like that. If gate or clock is 1, then Q is equal to D. So output is equal to input. This is called latch is transparent. And when G or clock is equal to 0, then we say latch is in memory mode. What that means is that the output Q is equal to the output. Means whatever is stored there, it stays there inside the latch. So this is storage. So basically a latch can store a single bit, okay, and it is also called level sensitive, which means it works on, for example, the levels. For example, if this is the G signal, it works on if G is equal to 0 or G is equal to 1. Okay, so it works on this level. The second thing is flip-flop. So flip-flop can also store a single bit. It can also store a single bit, but this is said to be edge sensitive. What that means is that if we have the clock signal like that, it works on the edges, okay. It's what we mean by work. It can change or store the bit on the positive or the negative edge. If it changes the storage on the positive edge, we call it positive edge triggered flip-flop, and if it changes on the negative edge, for example on the green one, then it is called negative edge triggered flip-flop. So the further details of the designs are in the upcoming slides. So let's move to the first one, which is the D-Latch. So as I told you that it depends on the gate or clock. So this is the gate or clock. Okay, so when clock is 1, the latch is transparent and D goes to the output, as I told you. And when clock is 0, the latch is opaque or in memory mode, which means whatever is the output, it stays the same. Okay, so for example, let's look at the gate signal. Here let's consider it from this point. When the gate or clock is 1, here it is 1. Okay, so this is our input, this is our output. Okay, so when the gate is open or clock is 1, what happens? Whatever is at the input, it comes here. Of course, after a delay. The delay is required for passing an input towards the output. So because there are transistors inside, those transistors takes a certain amount of time to propagate the signal. So after that propagation time, we will get whatever is at the input, it comes out at the output. Now here at this point, the input changes. Okay, and then again after some time, which is the propagation delay, it is called TPD. TPD means propagation delay. Propagation delay. So after a certain amount of time, it appears at the output. Okay, so you see here the output has become equal to the input. But let's see what happens when the gate changes to 1. So at this point, you see, at this point the clock becomes 0. Okay, and at this point the latch moves to memory mode. What that means is whatever is at the output will stay at the output. So we have a 0 at the output and it will stay as 0. Although if you look to the input is now 1. So the input is 1, but the output is 0. Why? Because the latch is in memory mode. Okay, the latch is in memory mode and it neglects whatever is at the input. So this is the operation of a D-Latch. Now let's go inside the circuit for a D-Latch. So before explaining whatever is on this slide, let me draw another circuit to open up your mind. For if you want to store a single bit, okay, we want to store 1 bit. It can be a 0 or it can be a 1. Okay, so let's see how we can do it. For example, if I have a NOT gate, which you know very well now, and I connect it like this. Okay, and this is our output. If I gave it, for example, a 0 here, the output will be 1, but this one is also connected here. Okay, so it will become 0 again. You see what's happening? There is this loop. Okay, at this point you see that this 1 bit is stored inside it is stored inside this loop. Okay, so this is like the main principle on which you can say, of course this is not the correct circuit, but this is just to show you how we can store a single bit just by using NOT gate. Obviously this is a very poor circuit for storing 1 bit, but it is good just to illustrate the concept. Okay, so this is basically, you can store a bit using feedback. Okay, so this was it. Feedback is the main concept that is used when you want to store a bit. Now let's move to an actual circuit of D-Latch. The actual circuit looks like this one. Okay, it has a multiplexer, a 2x1 mux, which you have studied in the previous lecture, and then we have a NOT gate, and then we have another NOT gate. It is connected to one of the input of the mux. So what happens is, if the clock is 1, then the multiplexer selects this input. Okay, and the bit goes to the words to Q and Q bar, but Q bar is connected here, so it goes here. Okay, but this path is closed because clock is 1. So we say that the D-Latch is transparent. Okay, now what happens if the clock signal is 1? Let's see what is that scenario. When the clock signal is 1, what when it is 1, yes, when it is 1, I think I have when it is 1, it is this path is selected. Okay, and let's transparent. And when it is 0, then this path is selected, and when this path is selected, it goes like this and comes back like this. So we have the loop. So when clock is 1, it is transparent. When clock is 0, it is in memory mode. Okay, what is the difference between this circuit and the circuit which was consisting of 2 NOT gates? The difference is that it has this clock signal, it has control. So it has the control signal. So the control, it means that you can choose when to change the latch from memory mode to transparent mode. So it was the circuit number 1. Okay, and the circuit number 2 is the same circuit, but it shows the detail of the multiplexer inside. So you see that if you consider this one, how it is implemented, it is implemented like this. So, and this circuit we have studied in the previous lecture, that how it is a multiplexer circuit. It is a multiplexer circuit with transmission gates. Okay, so this is just the multiplexer circuit and the feedback. Okay, so this is our D-latch. And again, the operation that I showed you in the previous slide is demonstrated here in some detail. So when the clock is 1, the multiplexer passes D, and this one is open as you have seen in the previous slide. So we have this path. So the latch is transparent. You can get Q and Q bar. And when the clock is 0, so the input is disconnected from the multiplexer, because the input was at the first line, one line, and we have this kind of feedback which enables us to store. So this is storing mode or memory mode, and that is transparent mode. So this is the operation in more detail. Let's move on to D flip-flop. So a D flip-flop, as I told you, is edge sensitive. Okay, and what that means is it works on the positive edges. Okay, what that means, that it goes on the positive edge, it samples the input, which is D, and it puts that sample at the output. So it goes to the input, it samples it, and it puts it at the output. Obviously you see some delays, and the delays are because inside are transistors and they are not ideal. They take some time for the signals to propagate, and I told you that that is called the propagation time. In the upcoming weeks we will go into much more detail inside of how the propagation delay comes, from where it originates. Okay, what are the components of propagation delay? But that will be after we know the internals of the MOSFET. So on the positive edge it picks up this. Okay, but you see here the input changes, the input changes, but the output stays the same. Why? Because the changes are only stored on the positive edge. They are only stored on this point. So storage only happens here. Storage only happens here. So at this point you go and you sample the input. So all the inputs changes are neglected, and then there comes another positive cycle, and then at this positive cycle it goes, it samples the input, okay, and it propagates it to the output. So the state only changes on the positive edge triggered. When the positive edge comes, it triggers the change. Okay, so this is the operation of a D flip-flop, and a flip-flop is a very fundamental and important building block of any digital circuit. You cannot think of a digital circuit without flip-flop. They are so fundamental to the design of digital circuits, and they are so important for the frequency. So in the initial lectures I told you, I put a question: what is the maximum frequency of a digital circuit? So the maximum frequency is determined by these flip-flops. So they have a very fundamental role which we will discuss in the coming lectures. But here I am just introducing the functionality of a flip-flop. The importance will be clarified in the coming lectures. So what's inside a D flip-flop? Inside, basically we have two latches. Okay, one is called master latch, and the other is called slave latch. So this is called master slave configuration. Okay, so one is master, the other is slave, and you see the clock signal goes to one uninverted and to the other as inverted. What that means? It means that both the latches are not transparent at the same time. I hope you know what is transparent. Transparent means that a latch can pass the input. So what I am saying is, because of the clock signal and how it is connected to the master and slave, it is connected with a NOT gate. Because of this interconnection, there is no point in time at which both the latches are transparent. If one is transparent, the other will be in memory mode or storage mode. If master is transparent, slave will be in memory mode. If master is in memory mode, slave will be in transparent. Okay, so this is how the master slave works, and this combination is actually very interesting, because in a digital circuit you can ask this question: how to detect the positive or negative edges. I mean, we are just using latch, and latch, as I told you before, that latch has nothing inside which can detect the edges. Latch is level sensitive, which means it works on the 0 and 1 voltage. Interestingly, the flip-flop is not level sensitive, it is edge sensitive. It means it stores the bit or changes the state at the positive edges or at the negative edges, not at the level. Okay, so you see, this is level 0, this is level 1, and this is the edge. So a flip-flop changes the state or stores a bit on the edge. And how it is made up of? It is made up of two latches which are both level sensitive. So how can that happen, that two level sensitive elements combine and they gave you something which can detect the edges? The answer lies in this magic configuration, which is called master slave configuration. Okay, so this is the circuit for the two latches connected. Okay, you see this is the master until this point, this is the master, and this is the slave. So we have this QM which is connected to the other slave. So let's see what happens when the clock is for example, when the clock is 0. When the clock is 0, okay, so this is clock bar is 1, okay, and this is clock, okay, this is 1, but this PMOS, what will happen to this PMOS? It will be off. What will happen to this NMOS? This will be on. So it means D will be connected to this point. It will go to here. Okay, so this is the path for D. Okay, what happens here? This is 1, this is 0. Okay, no, I think I made a mistake here. So this is clock is 0, so this is 0 and this is on. So both the transistors are on and D will propagate. Okay, let's come to the slave. Here it is again it was 0, so it means this is off, and here is clock bar, so this is 1, which means this is off. Now what that means, that until here the D comes, but D cannot move towards the output. D cannot move towards the output. What is the reason? Because slave is in memory mode. Slave is not transparent. Okay, so the input comes to this point, but it cannot go to the output because the slave, there is no path that is offered by the slave. So it has to wait. Wait for what? Wait for the time when the clock changes from 0 to 1. And what will happen at that point? This one was transparent, this one was in memory mode. At this magic point, the transparent master will go from transparent mode to memory mode, and the slave will go from memory mode to transparent mode. And when it goes to transparent, remember our D which is waiting here, this D will go to the output. Okay, so this was to illustrate that at no point in time the master and slave are transparent. If one is transparent, the other is in memory mode. On the next slide we have further details. Again, it is the same scenario. When clock is 0, what is happening? This master is transparent, the slave is in memory mode, but you see here the disconnection, so the input cannot propagate to the output. When we change this This is now in memory mode. This is now transparent. You see the loop is broken. The loop is broken, and here the loop is established. Okay, so let's see the timing diagram. So the timing diagram is something like that. At the point in time when the clock moves from 0 to 1, okay, what was happening? The master was transparent on 0. Master was transparent on 0, and it is moving to memory state. The slave was in memory state. So this is happening in point in time when you are changing the clock from 0 to 1. So this is happening in a point in time when clock was 0 and it was changing to 1. So what is happening at that point? The master is going to memory mode. The slave is going from memory mode to transparent mode. It means that at the middle, when D was waiting, D is allowed on this point. It is allowed, it is sampled, and it is allowed to go to the output. So okay, so it is sampled and it is allowed to go to the output on the positive edge. Then all the changes that are from here to here, these changes are neglected because there is no positive edge. Then again at the positive edge, the magic happens. It goes, picks up the input, transfers it at the output after some delay, and the state changes. Okay, so you see there is nothing inside this circuit which can detect the positive or negative edges, but the combination of these two latches gives you a behavior which feels like it has something which can detect edge, and this edge is so fundamental for digital design. You see, what is the importance of this edge? We say that that edge determines the time period. This is T clock. So T clock is basically 1 by F max. So if your processor is running at 3 gigahertz, what will be T clock? It will be 1 divided by 3 gigahertz. So that is the edge that we are talking about. The distance between two consecutive edges is your clock period, and it is so fundamental and so important that it determines the overall speed of your circuit. As I told you, we will go into much more details of how the maximum frequency of a circuit is determined in the later lectures. Okay, again there are some issues that can arise. One of them is this clock skew. this is basically a large, you can say a much deeper topic, but we will cover it very briefly here. So what happens is that all your design has flip-flops. Here we have two flip-flops. One is driven by this clock, and the other is driven by this clock too. And basically in most of the cases this is the same clock. But why it is shown like this? It is shown like this because to show what is clock skew. So clock skew is this, that you have hundreds and thousands and millions of flip-flops on a chip, for example inside a microprocessor. So basically you have, from where is the clock coming? The clock comes from a crystal. So this is like, let's say this is our crystal. The clock comes from here, and then we have this flip-flop, and then we have this flip-flop. Now you see this flip-flop may be very far away from this flip-flop. I mean, for humans this is no distance, but we are talking about things in the microelectronics and nanoelectronics domain. So this distance is large for very fast signals. This at the nanoscale, the slight difference in the clocks is dangerous. Okay, so actually what is the requirement? The requirement is that both these flip-flops should get the clock or positive edge at exactly the same time. But due to the clock skew, which is the delay due to the physical distance between two flip-flops, the two flip-flops do not get the clock at the same time, and resultantly they do not trigger at exactly the same positive edge. So ideally the requirement is all your flip-flops, whether they are 1000, 100,000 or 1 million or any number, they should change the state at exactly the same time. But due to the clock skew, this may not happen. And if that may not happen, if there is a delay, then there is something wrong that can happen. And what wrong that can happen is this one. For example, there is a delay in these two flip-flops. This is called clock skew. Due to the clock skew, actually at the output of flip-flop 2, okay, first you should get, so actually you should get something like that. You should get first Q1, and then after a certain amount of time the state changes and you get Q2. Okay, but because of the clock skew, the second flip-flop fires late. Okay, and what happens because of that? It sees first flip-flop change and capture its result. Because that is late, okay, what is happening here? First there was Q1 which came here, and Q1 should go outside, and then came Q2. So ideally it should come here and then it should go outside, like this one, like the Q1 then Q2. But when this is late, what happens is that this does not fire and it is waiting, it is late. So this one comes and replaces Q1, and only Q2 gets outside. Okay, so only Q2 gets outside. So this is called hold time failure. Why hold time? whole time because flip-flop 1 was not able to hold Q1 for enough time. Let me write this. Flip-flop 1 was not able to hold Q1 for enough time. Why enough? Because actually it should have waited for flip-flop 2 to pick Q1 and throw it at the output. But because flip-flop 2 was late to pick up Q1, the flip-flop 1 has changed its output from Q1 to Q2, and the flip-flop 2 mistakenly takes or samples Q2 and puts it on the output. So actually, because of the hold time violation, Q1 has been missed. Okay, so this is like a serious issue which can arise because of these clock skew violation. Now to deal with clock skew is in such initial lecture is difficult, because this is something on which people in the industry spends a lot of time. So we will assume in this course that all our flip-flops gets, so our assumption will be all flip-flops receives positive edge at same time. So this is not what is reality, but this is what we will consider in this course. So one very simple solution is that we will consider all the clocks non-overlapping. So for example, the flip-flop master and slave has a phase difference of, let's say they are out of phase, so when one is low the other is high. Okay, so in that case we are using two different clocks. They are not connected with a NOT gate. We are using actually two different clocks with a phase difference, so it reduces the chances of clock skew. Clock skew arises when you connect a single clock to a lot of flip-flops, millions of flip-flops. Then the chances of clock skew are more. But you can, if you are using two clocks with two different phases in the same flip-flop, it reduces or it eliminates the chances of clock skew. So this is one solution, but our assumption will be that there is no clock skew for this course. Okay, let me stop here. So in this part of the lecture we have discussed in some detail the design of D-Latch and D flip-flop, and I told you that we will come back to these two building blocks, at least to flip-flop, in much greater details when we will discuss the sequential circuits and how to determine the maximum frequency of a sequential circuit. So we will come back to it. We will come back to what is inside the propagation delay, how it is made, and all these details in the upcoming lectures. Okay, for this one.